Yeah, let's go back to the 90s. Let's do some cool, really super old stuff. My name's Justin. This is the talk that I wanted to see if the CrikeyCon website and the run sheet and the posters could actually fit on there, and they did, so that's good. Bit about me. By day, I do product security and computer security incident response, bit of AppSec, bit of corporate stuff, bit of network stuff. By night, I take money from companies who run bug bounties, or at least try to. And today we're talking about stack-based buffer overflows, save return point override kind of stuff. Who here has done stack buffer overflows before? Quite a few, cool. This is, going right back to the 90s and some pretty simple stuff. But so what we're doing is housekeeping, theory, demo, closing thoughts. It's super old stuff. It was kind of back in the 70s that we thought this should be possible. It was in the 80s we saw it exploited with the Morris worm. It was in the 90s that we got the seminal frac paper smashing the stack for fun and profit. So that came out in 96, 20 years ago, so it is super old stuff. It's not my own research. I didn't actually do anything cool. It's just my understanding of how this sort of thing works. So I meet a lot of people who say, I've always wanted to get into all that debugger stuff, the assembly stuff and that kind of thing. I just haven't really had a chance to try, or it looks kind of intimidating. So I'm wanting to try and just demystify how the stack works, how the CPU works, how memory works, and how memory corruption bugs can be exploited, just to try and take some of the kind of scare out of it and say, hey, look, if there's plenty of resources on the internet to just give it a go, pull down some old binaries and run through some tutorials, it's pretty achievable stuff, because computers are deterministic. It's not, spooky black box that we don't know what's going on inside. Once you kind of get to know the patterns of assembly and the patterns of exploitation, it's the same thing over and over. It's pretty predictable, pretty standard stuff. And once you get to know the patterns, it's totally achievable. Today we're running in what I call easy mode. So there's no SLR, no dep, and no stack canaries enabled on the binary. If you don't know what these are, we'll go through what they are at the end and how they would totally harsh our mellow if they were on. But even though this is old stuff, hacking in easy mode is still super relevant, because you kind of need to learn to crawl before you can walk. And by learning the simple stuff, it kind of builds a platform atop which you can then start to add in the techniques to evade or defeat ASLR, dep, and etc. One last note, we're running on a 64-bit, more or less mostly, I think, up-to-date Windows 7 box. So it's 64-bit, but the binary is a 32-bit binary. When you run 32-bit binaries on a 64-bit Windows box, you get you get this thing called WoW64. It's Windows on Windows 64. It's an emulation layer, so that the 32-bit binary, from its perspective, it runs in 32-bit mode. Everything around it looks like it's 32-bit. So when you run a 32-bit binary on a 64-bit OS, you got to hack like it's 32-bit. So even though it's a 64-bit machine, we don't need to worry about 64-bit stuff. So stack buffer overflows are a type of, did I bring my water bottle? Yes, I did. Type of memory corruption bug. And so the idea is there's a program that will take user-supplied or attacker-supplied data and work with it in memory. And if the user can supply some tricky data that the program wasn't designed to handle or handles poorly, the idea is you corrupt things in memory and then take advantage of that to take control of the program. So it's a type of memory corruption bug. And it's to do, there's a lot of different types of buffer overflows. Stack buffer overflows are particularly to do with the stack. So there's heap buffer overflows, there's all sorts of different places it can happen. We're going to focus just on the stack ones today. And in particular, there's a couple of ways you can exploit a stack-based buffer overflow. We're going to be focusing on what's called a save return pointer override. So it's a very particular type of a particular type of a particular type of memory corruption. So before we get too into the weeds of assembly, there's a few things we need to cover. Registers. Registers are kind of like the variables of the CPU. They're little slots in 32-bit CPUs or in 32-bit mode. They're 32 bits wide. And they hold data. The CPU uses them to hold data temporarily, be it a pointer to something in memory, like I want to keep track of where that is, or a number it needs to add or divide or whatnot. So the first row here, EAX through EDX, ESI, EDI, they're mostly general purpose-y kind of things. There's some conventions around how some of them are generally used. But for the most part, the CPU can use them as it needs to kind of keep stuff in memory or keep stuff in its register that it wants to remember for a short term. EBP and ESP, that first row we're not going to focus too much on today. We'll see them, but we're not going to worry about them. EBP and ESP are pretty important. They're to do with the stack, and so it's how the CPU keeps track of what the stack looks like, and we'll talk about what the stack is in a minute. EBP we don't worry too much about today either. You'll see him being used, but he's not too important. ESP is super important today. So ESP, what it does is it always tracks the top of the stack. And we'll talk about the stack in a second. But just keep in mind that the CPU will always use ESP to point to what's called the top of the stack. EIP is kind of like the teleprompter on AIM command. Whatever's in it, the CPU will go to and execute. It uses it to keep track of where it's at in executing the program, and it always points at the next assembly instruction that's going to be executed. So what we have to do is take control of EIP somehow and point it at something we control, and then bring some shellcode in and execute it, and away we go. So the stack is just a particular area of memory that's been reserved to function in a certain way. So it's not stored anywhere special, it's just in RAM. But there's kind of some semantics around how it tends to be used and how the CPU has some specific things, some specific instructions to use the stack in the way it does. So on the right-hand side, this is how we typically diagram and look at memory. And it can take a bit to get your head around the fact that it's laid out with the smaller parts of memory, the lower addresses at the top and the bigger ones at the bottom. So you've got to kind of tilt it this way to think of it linearly. So ESP always points, as I said, to the top of the stack. We'll just start ESP somewhere and run through this assembly. And as I said, EIP always points to what we're going to execute. So we're going to push the numbers 1 through 4 onto the stack. And you can see as we do it, ESP automatically, when it gets a push instruction, moves up in memory. It moves up towards lower addresses. So it's actually writing backwards if you think linearly. It's just the way the stack works. So we've pushed, the stack is kind of a last in, first out. You can kind of push plates to the top, and then you can pop plates off the top. You can look in the middle of the stack and access it directly, but when you're pushing and popping, it kind of goes up and then it goes back down. So when you're popping, we're going to pop what the ESP currently points to, number 4, into the register EBX on the lower left there. We're going to pop number 3 into EDX and so on and so forth. So you can see that as you move through, as you move forward, as you pop, ESP automatically jumps down to the next higher address as it peels stuff off the stack. And even though it's not important, you'll see that all the old stuff is actually kind of left hanging out here. The ESP moves to kind of say this is the new top of the stack, but this stuff will get overwritten when we get a new push come along, so it just kind of hangs out there and eventually gets overwritten. So that's pushing and popping. Yeah, as I said, it grows backwards linearly through memory. So if we were to actually get this and represent it linearly, we'd get the number 4, 3, 2, 1. So even though we pushed number 1 first, it's actually towards the end of memory and the 4's towards the beginning. One more trap is Intel is what's called little endian architecture. So things like numbers and pointers get put backwards, so the bytes actually get reversed. So this here, 00000004, comes out as 04, 000000. Numbers and pointers do that. Strings and code go front to back, just to keep things interesting. So that's cool. That's how the stack works, but why is the stack used and what's it used for? So it's used during the execution of a compiled program to keep track of what's called stack frames, and stack frames are owned by functions. So as you call different functions, as the program executes different functions as it goes, the stack will grow up to include 2 things. First of all, the data, the local variables of each function get put into the stack. The second thing it gets used to keep track of is some bookkeeping and some accounting information and some control flow information. Namely things like when you're about to call one function, it's kind of like, okay, I'm going to go and execute this, but when I'm done, I want to come back to here. So the CPU will push what's called the return address, we'll see it in a second, to the stack as a bit of a kind of a bookmark. I've got to come back to here later on. So for example, some pseudo C code and some pseudo assembly. What we're going to do is step through this in the assembly version. And all it is you've got the main function, because execution with C programs starts with the main function. It's going to execute, or it's going to call the foo function, and the foo is just going to have this local variable, just a character string, and then it's going to fill it with A. I didn't want to write that code. And then when it returns, we expect this return to cause execution to actually finish off the rest of main, which is just throw it a bugger breakpoint. So it's kind of, when you call a function, the CPU needs to go to and come back later on. And this is how it achieves it. When EIP is pointing to a call instruction and that call instruction gets executed, 2 things happen. First of all, EIP Screensavers are hard. There we go. First thing that's going to happen is EIP is going to get updated and point to the new place it's going to, and it's going to then execute that. But the second thing that a call will do is it will push the address of the next instruction, in this case 0005, onto the stack to kind of go, I'll remember this, I've got to come back to it later. So if we step, then we see EIP jumps down a bit, and the return address, 0005, gets saved to the stack as what's called the save return pointer, and this will get used later on to know where to go back to. So then, this is the foo function here. Push EBP, move ESP, or EBP-SP, is what's known as the function prologue. It's a little stack dance that we don't worry too much about today. So we'll just step over that. You'll see that the EBP arrow moved around, the ESP arrow moved up because we pushed this new thing to the stack, but we won't worry too much about what it is. The next thing that functions do is they subtract a value from the ESP register. And because when ESP goes this way, it gets smaller, the effect of just directly subtracting 16 or 0x10 from the register is that ESP is going to just jump up. And it creates this little gap here on the stack. So this whole thing here is called the stack frame. It's the stack frame that belongs to foo. And if foo was then to call other functions, you'd see more stack frames kind of grow this way. So this space here is what's used for the local variable, in this case, that char my string. The space that gets created by this hole is for that string. So if we were to just fill it with A, whoop, I skipped too many. Fill it with A, we'll see a whole bunch of A's appear, terminated by a null byte, right before all this kind of stuff, all the saved bookkeeping information. And then towards the end of the function, what we do is we pull ESP back down to where EBP is. We pop the saved EBP. That's not too important today, but this is the important bit. When we return, ESP, whatever ESP points to, this pointer here, because that's what we pushed to the stack when we did the call, that's where we're going to go back to. So if we step, then sure enough, 0005 is what we're executing next. And int3 is just a debugger breakpoint. If a debugger is not attached, it won't do anything, I don't think. But don't leave them in your exploits because they can cause trouble if they butt up against shellcode. The int3, if there's no debugger attached, does nothing. If there is a debugger attached, it just causes the debugger to go, I'm going to pause the program now. So if the debugger was attached, it would break the execution. So if we were to lay this out end-to-end in memory, then what we see first of all is the string of A's. 0x41 is capital A ASCII. We'll see all the A's, and then we'll see the saved EBP, which we don't care too much about today. But then we see this is the save return pointer. So the idea of a stack-based buffer overflow save return pointer overwrite is what if these A's, what if the attacker could control how many A's got written to that local variable, written to the stack, and could overwrite the saved EBP, that's, yeah, whatever. But if you could overwrite the save return pointer, then when that return came around, you could actually specify the address that the function will return to. And that's how you get control of EIP. And then it's just kind of a little bit of a song and dance as to what to put somewhere, how to get EIP to point to that thing, and then you're off. You can execute your own assembly. So now we're going to do a demo. Demo gods hopefully will smile upon us. There's 3 bits of software we'll be using. First of all, Immunity Debugger. If you're going to go home and do some tutorials and this kind of stuff, which I recommend you do, it's good fun. A lot of people talk about Ollie Debugger. So Ollie was a debugger, is a debugger, but it's quite old, and Immunity is more or less the replacement, the more modern version it's a rewrite of Ollie by Immunity Security. And then the other thing we're going to use is Mona. Mona is from Call Encoder. It's a plugin for Immunity. It's geared towards exploit dev kind of stuff. And we're going to use a few tools from Metasploit as well to help us out. One more slide. Can everyone read this? Yeah? Cool. This is a small program I wrote for the demo purposes today. Benefit knowing is I know how to break it now. So that's totally cheating. But this is the code for a binary. By the way, I'll be releasing, actually already have released on GitHub, these slides, the code, the binary, and half of the PDF that I didn't get around to finishing. The PDF will walk you through this demo, so if you kind of have trouble keeping up but you want to give it a go, the PDF will help you replay the demo at home. So this is the code. It's a very cut down version of the code. I've kind of snipped out the boring stuff. So the main function is where when you run this binary, execution will start. That's just where I've put all the copy-pasted stuff from MSDN to set up the network socket. I'm a copy-paste developer, not really a developer at all. And then what it does is it starts listening on port 31337, accepts connections off the network, and when it gets a connection, the program will kick off a new thread executing this handle connection function. So you can have multiple connections going on at once, and that's totally fine. Handle connection, what it does is it reads off the wire, and for each line that it gets sent, it sends that line and the client socket handle to this do response function, and this do response function is where the fun happens. So what do response is going to do is it's going to reserve a 128 character buffer on the stack, and then it's going to sprintf into that response buffer. So what sprintf does is it's going to take this hello %s bang 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 string, and it's going to put the client's name instead of the %s with the line that you sent, and then it's going to store that resulting string in this buffer. This is where we have the opportunity to send a whole ton of A's down the wire and see what happens, and then it just spits it back over the network. And then the function returns, and so when it returns, normally you'd expect execution to come back up to right after this do response call, unless you've managed to sprintf something else into response and have it overwrite the safe return pointer, and away we go. Let's see how we go. Oh, come on. My machine is not popping a shell. That's incredibly concerning. There we go. Ah, full screen. That'll do it. We've got 4 shells now. Okay. So we'll launch Immunity Debugger, and inside Immunity, we'll load the compiled version with no SLR, no dep, none of the hard stuff into the debugger. So this is Immunity. We can all read that. Yeah, nice big text mode. It's kind of hard to fit it all on the screen. But this here is the disassembly. So this is the code, the assembly that's going to be run. These are the contents of the registers because the program starts up paused. This is the stack, and this is just a dump of memory. So we mashed the play button a couple of times, and the program starts up. It's not at all what I wanted. And then we can just we can connect using Netcat. This is my host machine. This is a VM, and we can send CrikeyCon. It'll reply hello CrikeyCon. We can send a bunch of A's. It'll send back hello a bunch of A's. So instead of sitting and just doing it all in Netcat, we're going to kick off a Python script to manage the connection for us and to be able to send more interesting things than we could just sit here and type ourselves. So the first thing we do is we connect to the remote host. We can read that. That's all good. Yeah. So we connect. Let's just create a new empty string and then add to the end of it, let's say 1024 A's, and then a new line. And let's go and cram that down the wire, and we won't bother kind of receiving back whatever we get. We're not too interested in that. Alrighty. So the program's running. If we were to run this script, what we see is the debugger says down the bottom, actually it's cutting it off. We get an access violation when executing 41414141. So now 41414141, when you're breaking stuff, is always good to see. It's the hex code for AAAA, or the ASCII for AAAA. So what we managed to do is the good thing about these is you can generally exploit them by feel as well. The PDF goes into digging into the binary and having a look at the exact instructions and what's going on and stepping through it. But we know that based on the idea, if you just trust me, based on the idea of local variables, the stack, if we write a ton of A's, it'll overwrite that save return pointer, and then eventually when a return gets hit, it'll go to whatever kind of creamed that 4-byte area in the stack. Immunity is telling us that the program crashed because it tried to execute for one, and there's nothing there to execute, which is good because it means that, yeah, does that make sense that we smashed that safe return pointer, it tried to go there and it crashed? Cool. So what we need to do next is we need to think about exactly which 4 bytes of that 1024 A's are what ended up overriding the safe return pointer and ending up inside EIP. It's not at all what I wanted. So there's a tool that comes with Metasploit we can use to find this out. Either we could kind of sit here in the stack and count them all, but Metasploit comes with a tool called pattern create. And what it does is takes one argument, takes an argument of how many characters of a string you want it to build, and it spits this back. This kind of non-repeating pattern of ASCII characters, and no 4 character string in this sequence in this string is the same. So based on what ends up in EIP, we should be able to kind of figure out how far into this string it was if we send this instead of the A's. So instead of the A's, we'll go and so we're going to send empty string appended to it, this pattern appended to that a new line, and see what happens. So we'll rewind or we'll restart the process and hit the play button a couple of times. And running this script, we get a different crash. We get EIP not having 41414141 anymore, but instead 39654138. And so what we could do is we could, there's a tool called pattern offset, which you could kind of give it that number. It'll tell you, oh, that string happens to be so far into the sequence. But Mona gives us a really nice little feature called find MSP. It stands for find Metasploit pattern. And what it's going to do is it's going to search memory for all instances of what look like that cyclic pattern and tell you about what it saw. And it gives you a whole bunch of info, which is interesting for certain cases, but we're really looking for this. It figured out that EIP contained a subset of that pattern at offset 146, so that we know that it's actually 146 characters into that buffer that we end up overriding the save return pointer. It also tells us that ESP points at offset 150, which is right after the save return pointer, which makes a lot of sense. And this is a pretty common pattern, because when a return gets done, ESP, kind of slides down to the next biggest address on the stack. So it makes sense that ESP just so happens to point right after that interesting save return pointer. And we're going to end up using this as well in our exploit. So based on this offset of 146, we'll touch up our exploit to test it out. So instead of the Metasploit pattern, we'll send 146 A's, B, and so we expect that this is the save return pointer overwrite, and it'll go into EIP. Let's send like CCCC, and we think that ESP points here. We'll see, buff plus equals, and we'll send enough D's to take this buffer out to the total length of our original buffer. It's just a good habit to kind of keep the total buffer length consistent. So we'll just subtract the length of buffer so far, and rewind the process, and send it off. Nope, we'll hit the play button, and send it off. Cool. So this time, instead of a crash on 41414141, we get it on 42424242, which shows that we've accurately managed to overwrite that save return pointer, and now we can kind of put what we want to put there, and the CPU will go off and try to execute what's at that address. Furthermore, we see that ESP does indeed point to our 4 C's followed by a bunch of D's, so it's also confirmed that fact. So now the next step generally is to think about what's called bad characters, because so far we've been sending readable ASCII strings, but we haven't been sending anything interesting. If we want to start sending assembly that is going to end up executing, we want to make sure that those characters that we want to use as part of that assembly are valid and legal in terms of what the program accepts, because there's some programs that won't let you send certain things over the network, or when you send certain characters, it might truncate your string, corrupt your string, it might substitute one thing for another. There's an iterative process you can go through for finding these characters. I don't have time to sit here and iterate through it today, but it's in the. I think it's something that's a to-do in the PDF, which I'll do this week. So the process would be to send all the characters, 0x00 through 0xFF, and kind of try to find out which ones the program doesn't like getting. But I can tell you that for this program, the null byte 0x00 is going to be definitely bad. A lot of string-based buffer overflows. 0x00 will be a bad character. You can't send that because that's the string terminator for C programs. If you send that, then the rest of your buffer kind of won't make it through to where you want to be. The other character that we couldn't send in this payload is a new line, 0x and 0a, because that's what kind of delimits the commands you're sending to the server. And if you send that, it'll chop your payload in half and process them separately, and the bug won't trigger properly. So skipping the process, we know that those two characters are definitely bad, and that's actually the only bad characters for this binary. What am I doing? It's not what I wanted. So we'll just have to keep in mind that as we progress, we can't use those two characters. The next step is going to be thinking of somewhere to put some shellcode or some assembly, some malicious assembly in memory that we want to get executed. Where are we going to put it? Where are we going to put it in our payload? Where will it go into memory? And how are we going to get EIP to point to it, to execute it? So with this kind of pattern of exploitation, generally the easiest thing to do is to put the shellcode at the place at which ESP will point to at the time you get control. So right after the save return pointer. And into the save return pointer overwrite slot, you could put the address of the stack. ASLR, ignoring it. The thing is with the stack, it tends to be much more variable than something else, which is the binary contents in memory of the original program. For example, this is a threaded application. If you were to connect twice, you've got two different stacks in two different areas of memory, you might not know which one you're on, so you might not be able to predict what the direct stack address of your shellcode is. But if you could predict it, you could just go and put that address in directly. Actually, no, you couldn't. There's null bytes, so you can't even do that. Instead, the idea generally is to find a trampoline that's part of the original binary code, part of the original assembly. So if we were to find somewhere inside the program itself, which we know is in memory, and because there's no SLR, we know where it's going to be, if we could find the byte sequence for jump ESP, get EIP to point towards that, execute it, it'll cause EIP to jump to the address that's in ESP. So did I say jump ESP? Yeah, find a jump ESP, overwrite the save return pointer with the address of that jump ESP, EIP will go there and bounce back and execute the stack. So again, Mona gives us a function to find this. From the crashed state of the binary, bang Mona, jump to the register ESP with the bad characters 00 and 0A. Let's tab across to that. And Mona tells us that it found two pointers. These both look good, there's no bad characters in them, and these are memory addresses of jump ESPs inside the original program. Put a right click on one of them and follow in disassembler, and sure enough, there's a jump ESP there. So if we execute this, then execution will bounce back to the stack and execute that instead. So what we'll do, I really should rebind that key. Instead of BBBB being our save return pointer overwrite, we'll put this address backwards because little endian and stuff just to make life interesting. So it's going to be hex C3, hex 14, hex 04, hex 08. There is a quicker way to reverse, put things in little endian form in Python, but just for verbosity's sake, I'll actually type the whole thing out. And instead of CCCC, which is what ESP points to, we want to put a small program there or some machine code that will be executed when this happens. In this case, what we'll do is we'll just go and put hex CC. Hex CC is that int3 breakpoint. Because there's a debugger attached, if that hex CC were to be executed, we wouldn't see the crash we normally see. Instead, Immunity will just say, hey, I've hit an int3 breakpoint. So we'll rewind the program, mash play, save the exploit, run the exploit, and there we go. Instead of a crash, Immunity now says it hit an int3 command at this address. So if we look, thank you. It's not even the good stuff yet. If we look in the disassembly, we'll see this CC here. It's kind of hard for debuggers to disassemble backwards. We'll see the CC is what we executed, and all these 4444444s is the hex code for the Ds. So we're about to execute a whole bunch of Ds, which is kind of boring. It's just going to increment ESP. Actually, it'll probably crash pretty quickly because of that. So instead of a whole bunch of Ds, we need some malicious assembly code to put instead of them to be executed. And there's another tool that comes with that. That's called shellcode, by the way. Malicious assembly is called shellcode. Metasploit has a tool, MSF Venom, which generates shellcode for you. So we want the payload, Windows, Meterpreter, can't spell, reverse TCP. It'll connect back over TCP to establish the connection. We need to put our IP address in it, 172.17.24.1. We'll get it to do over port 4444, the standard. And the exit, we need to set the exit function because the shellcode needs to know how to basically stop the process from running off and executing the rest of the stack when it finishes. The default is exit func process, which just quits the whole thing. But because we know it's a threaded application, we'll just get the shellcode to just kill the thread that we hijacked, and we'll get a shell back, and the program keeps on running, and everything's great. So exit func thread. Bad characters, we need to tell Metasploit, don't put hex 00 or hex 0A, and we want it in Python format. Python format, the formatting of shellcode doesn't affect the contents, just how it gives it back to you, so you can copy paste it into your exploit. So we'll copy paste, this is all malicious assembly that will connect back to our computer and start a reverse shell up. I like to copy everything, including how I generated the shellcode, and then just comment it out for documentation's sake. So up here, before the socket got created, we'll paste that in. We'll comment out this here. And because I like to call my exploit payload buff, Metasploit also likes to use the word buff. So we'll just do a search and replace to get rid of that. I'll call it SC Meterp. So now the shellcode is this string called SC Meterp. So this is malicious assembly. When it gets executed, we'll get a connection back. So instead of the int3 breakpoint, buff plus equals shellcode Meterp. So what we're going to be sending over the wire is 146 A's. That's just the padding to take our payload out to the length before the save return pointer overwrite. We'll smash the save return pointer with the address of a jump ESP. So when it gets returned from, when this function that handles this data gets returned from, it'll go execute a jump ESP, bounce back, and execute SC Meterp. That will execute and connect back to us and start up a shell. There's one more step that's left. And this is a tricky one. Shellcode. Shellcode encoding. Because we said that we don't want to use hex 00 or hex 0A in our shellcode, Metasploit had to encode the shellcode and kind of do some tricks to make sure that it was not containing those characters. And it does that by encoding it and then putting a little stub before the shellcode. So the first little bit of that shellcode is going to be a decoder that goes through and rewrites the rest of the shellcode back to what it should be with the bad characters in it. The issue with that decoder is it doesn't just push to the stack. It actually blows up the stack around ESP a little bit, using a technique that it needs to do to find out where it is in memory. Because ESP is going to be pointing to the beginning of the shellcode decoder at the time that it does this operation, it's going to destroy itself and actually shoot itself in the foot when it starts decoding or trying to find out where it is before it starts decoding, and you get corrupt shellcode and crashes. There's a couple of ways to fix this. There's the lazy way, which I'll do today, which is just to chuck about 16. I don't think you need 16, about 14 I think does it as well. 16 NOPs, so hex 90 is how am I going for time, by the way? 5 minutes, okay. Hex 90 is the assembly code for NOP, which is just do nothing, and so the CPU is going to execute 16 do nothings. But the effect of that is that ESP will point to those 90s, they'll get executed. ESP will still point to the beginning of them. Then the shellcode, when it executes, just blows up some useless NOPs, and we don't really care. There's a much cleaner way of fixing this up, and it will be in the PDF when I bother finishing it off. One last step. We need to start up a Metasploit interpreter listener, because when it connects back, it kind of needs to feed more brains to the payload, the process being exploited. So we'll start MSF console, can't spell. So I'm not actually using a Metasploit exploit, we're just using it to catch the shell that phones back home. So using exploit multi-handler, we're going to set the payload here to Windows interpreter reverse TCP. Set our own IP address. There's a reason for that, because it needs to bake that into what it sends back. Set the port, set the exit func again. And so Metasploit's now listening for the connect back from the exploited binary. Let's cross our fingers, close the debugger, and just run the binary raw by itself. Make sure the exploit's been saved. Run the exploit, and shabow wow. Shabow wow. So now you've got the binary that you exploited, it's phoned home back to you, giving you a interpreter shell. Interpreter gives you cool stuff like upload file, download file, do all sorts of crazy stuff. You can just drop to a command shell from there and poke around the system and cause trouble. So that's the demo. And I think I've got a few slides left that I'll see how quickly I can power through. It's only lunch, we're not hungry. So that was too long, you didn't care. General idea, trigger the bug, just send lots of A's, get a crash at 414141, be happy. The next thing you do is you discover your offsets using that Metasploit pattern that doesn't repeat itself. Once you find your offsets, just test them to make sure you didn't stuff up, make sure you can get that BB nicely into the safe return pointer overwrite. Discover your bad characters, it's like a trial and error sort of educated thing you iterate through and try and figure out which ones suck. And there's a function in Mona that you can use to compare what you think will be in memory to what is actually in memory, and that's the tool you can use when you're doing this trial and error. Think of where you want to put your shellcode, where ESP points to, or where another register happens to point to at the time of the crash or the hijack is a pretty good place, because you can then just bounce off something in memory, a gadget in memory. Use your control over EIP to divert execution to that trampoline, which will then trampoline back to the stack. Generate your shellcode, account for the decoder stub just destroying itself if ESP points to it, set up a listener, run your exploit, catch a shell. Simple, right? The solution, this is, okay, I didn't mention, this is mostly an offensive talk, it's an attack talk, this is the stuff that can go wrong. I'm not a software developer by trade, I'm a breaker by trade, so I just tend to ruin people's days and say, you fix it. But as far as I understand, and this is not coming from a developer, this is just my understanding, the way to fix this, a lot of people kind of, and I'll get to this in a second, a lot of people think, but ASLR and DEP make it hard to exploit or impossible to exploit. They don't make it impossible. They're a pain in the butt to get around, but you can't rely on them for security. If you know there's a bug in your program, fix the bug. If you're just program defensively. Never use stuff like sprintf unless you're really certain or really dangerous. There's replacement functions like snprintf, which takes an extra optional argument to say, hey, look, sprintf, I know you're excited, I know you might be told to copy a whole bunch of stuff, but I need you to stop after this many characters, and it's like a safety net for if it tries to run away on you. So use safe functions. I'm pretty sure that if you try to use sprintf in Visual Studio, it complains at you, so I had to turn the complaining off. So listen to your compiler. If your compiler's telling you you're using unsafe functions, don't use those functions. There's often replacement functions. But yeah, use bounded memory copy functions, string copy functions that kind of have that safety net of, hey, don't get too excited.
Aren't they just like SSL warnings though? You just click through.
Yeah, just click through,
Click
yeah.
through. It's fine. Whatever, YOLO.
There's a common problem, I think, where not just developers, anyone in IT who kind of has a problem just turns features off until it works, and you don't even backtrack to turn the irrelevant stuff back on.
A warning? Who cares?
Yeah, warning, who cares?
Error? Different story.
Listen to your compiler. And also you've got the option of things like static code analysis tools to run over your code to look for common errors or patterns that it thinks look suspicious. There's getting app reviews done by an AppSec professional, that kind of stuff. As far as the bugs you don't know about, this is where ASLR, DEP, and stack canaries come into play. So ASLR, DEP, stack canaries, they're compile time and or runtime mitigations against these kind of errors from actually getting exploited. It tries its best. What ASLR does is every time the program or the DLL or whatever that's compiled with ASLR gets loaded into memory, it gets put at a random location. So what that would have done to us today, it would have made it impossible to predict the location of that jump ESP trampoline. Also, the stack will then randomly move as well, so it makes it impossible to predict pointers that you can use to bounce off of or whatnot. DEP and NX, They're the same thing, just different words. What they do is they basically are a way of telling the CPU, I know you're really keen on executing whatever EIP points at, but I'm going to mark certain areas of memory as being executable or not. And if you ever get tempted to, I don't know how it's going to happen, but if someone manages to stick something in EIP that points to a non-executable area of memory, I know you like to do your job, but just crash. It's not worth it. So NX is a way of saying, hey, look, this sort of stuff, this area of memory, I don't want getting executed. Stack canaries is another thing that would have stopped us today. Oh, and yeah, NX would have stopped us from executing that shellcode on the stack because the stacks would have been marked as not executable. Stack canaries, little 32-bit, I think they're 32-bit, tokens that get put at the end of stack frames between the local variables and that bookkeeping information. At the beginning of the function, a per invocation of the program random value gets slotted in between the local variable space and that bookkeeping space. At the end of the function, before the return gets done, that canary gets checked to see if it has changed between the beginning and the end. If it has, it means that something has overwritten it and possibly overwritten stuff behind it, so the program just crashes as a personal safety kind of activity. If you want to learn more about this, and it's a lot of fun, I love it, do call encoders tutorials. They're brilliant. They're Windows exploitation. They're using Immunity. They're using Mona. Just search Google for Call tutorial part 1. They're on the Call encoder on the Call team blog. They're really good tutorials. There's like 10 or 11 of them that actually do take you from the simple stuff like today through to starting to defeat things like ASLR and DEP and doing all sorts of cool stuff. Great tutorials. Any questions?